All right, let's get started with the fifth lecture. So, a brief review of what we did last time. Um, oops. So, last time we talked about the parallel axis theorem, which allowed us to relate the moments of inertia around different parallel axes, one being in some arbitrary place and the other going through the center of mass. So, the expression we found was, let's say, for some object that can rotate around some axis here, and there's another axis going through the center of mass, which is, let's say, here. We found that I is equal to ICM, moment of inertia around the axis that goes through the center of mass, plus m, the total mass of the object, times d squared, where d is the distance between these two axes. So we had a little bit of practice with this theorem. And then we started talking about torque. So torque is a quantity that tells us how effective a force is in causing rotation, right? So we talked about torque, and we built some intuition. So we figured out that the things that matter are, well, how large the force is, how far from the axis of rotation it's applied, and what is the direction? What is the component of the force perpendicular to the rotation arc, the line connecting the point where the force is applied to the rotation axis. So let's say I have an axis here, a distance r away, I apply a force F. Well, if I can decompose this force into two components, right? So I can find the component, let's say, in the direction of this vector r from the point where the force is applied to the axis of rotation. So this doesn't do anything. There is this component that's important, the component perpendicular to the rotation r. So if this angle here is theta, the angle between, or let's call it phi, the angle between the force and this vector here, from the axis to the point where the force is applied. Well, the magnitude of the component perpendicular to the arm is going to be F times sine theta, right? Sine of theta is the opposite divided by hypotenuse in this triangle here. So this from here to here has a length F sine phi. Okay. So tau is defined as R F sine phi. So let's keep going with this. First, a force can cause rotation that's counterclockwise or a rotation that's clockwise. And again, similar to angles and angular velocity and angular acceleration, we picked a convention that the counterclockwise direction is positive and clockwise direction is negative. So this torque that's rotating my object in this direction, so this is the axis, the force, the perpendicular component is in that direction, so it wants to cause a counterclockwise rotation, that's positive. So now if you have, let's say, a force acting in a different direction, so let's say that's your axis again, this is r, you have a force kind of going here. So now let's say this angle is phi. We can find the component that's perpendicular, so it's going to be again like F sine phi, but tau here, because it wants to rotate the object in the clockwise rotation, is negative. So that's our convention. So using this convention allows us to add different torques on an object and find the net torque. So if you have, let's say, I don't know, so let's say that's your axis, you have a force of some magnitude here, and then halfway you have a force twice that, so let's say that's 2F. This is L, this is L, this is F. So this one will cause a torque of F times 2L. It tends to rotate the object this way. This one will cause a torque of, again, 2F times L. So the net effect is that the object won't move. So the net torque is 0. So the sign of torque is quite important to keep in mind, and the way we just do it is we visualize like which direction the object tends to move due to the application of that force, and if it's counterclockwise, we assign a positive sign. If it's clockwise, we assign a negative sign. All right. So you may have noticed that that we can like view, so we viewed the torque as the component of the force that's perpendicular to the arm times the length of the arm. But there's another way to visualize this. So let me go back to this picture, right? So again, let's say that's the axis. This is R. This is my force. And this is the angle phi. All right, so let's say instead of thinking about the component of the force that's perpendicular to the axis, I think about the that's perpendicular to the arm of rotation, rather. I think about the component of the arm of rotation that's perpendicular to the force. So consider this distance from here to here. Again, what is this length from here to here? If that's R, if that's phi, then this angle is also phi. So this length from here to here is R sine phi. So we have this alternative way of thinking about torque and visualizing it. It's just, we project kind of our arm in a direction perpendicular to the force, and then it's like, again, r sine theta, this length times the magnitude of force is the same thing, right? So tau is again r sine phi. I apologize, I said theta before. I don't know why exactly I keep saying theta, but r sine phi times f. So these are two ways to visualize the same torque, right? So you can imagine maybe this force acting on some shorter distance, or a shorter or a smaller force, the component perpendicular to the arm acting at that point. They give us the same thing, and that's having this dual picture in mind is quite useful sometimes. So for example, let's say you have two forces, right? So let's say I have some rigid body. And let's say you have two forces acting on two different points that are on one line along the direction of the force. So let's say I have F here, and let's say the magnitude of these forces are the same. They're in the opposite direction, same magnitude. So they act on 2 points that are along the same line, and the forces are in that direction. But otherwise, the places the forces are applied with respect to the axis of rotation, and also the distance between the points where the forces are applied are arbitrary. So I have some axis of rotation somewhere here, for example. Okay, so one can try to do a bit of geometry, and let's say you want to find the net torque due to these forces. Well, yeah, I can imagine like this here is R1, this here is R2. So I can try to find these angles, calculate the individual forces find the component of the forces perpendicular to R1, find the component of this forces perpendicular to R2, and add them up using the first way to visualize this, taking the component of the forces perpendicular to the arm. Or alternatively, if I think about this second picture, taking the component of the arm perpendicular to the force, well, the forces are along this line, so that's the component. Let's call it R. And it's the same, right, for both of these forces. So that's cool. Therefore, we find the torque is going to be, so let's call that magnitude F. Right, how big the force is. So F1 is causing counterclockwise rotation. So that's positive, and it's FR, the component of the arm perpendicular to the force. F2 is causing clockwise rotation, and the magnitude is again FR, so that's 0. So it's kind of a useful observation if you have two maybe action-reaction forces, if they come somehow from Newton's third law or something like that. Regardless of where they're applied, they're going to give net force. They're going to give net torque. So it's useful to have these two ways to visualize. All right. So let's keep going. So that was, again, our definition of torque. So let's take a few seconds and think about this problem. And then, so pause the video, and when you're ready, we start and we talk about it. Okay, so what is the problem asking? So it's asking, there are two forces acting on this wheel. There's a pivot point at the center of the wheel. And we're asked to identify the force that would give a net torque 0 if that force is applied at point P. All right. So the force at the pivot, the distance to the axis of rotation is 0. Right? So that's not giving us any torque. So we can forget about it. The torque at the edge of the wheel, here, this one, it's causing counterclockwise rotation. So it wants to rotate the wheel this way. And the torque is, well, the magnitude of this force times the radius of the wheel. So first of all, we want the force at P to cause clockwise rotation, right? So it must have a component upward to give us a negative torque that wants to cause clockwise rotation to cancel out this positive torque from this force at the bottom. And then it's applied at a shorter distance to the axis of rotation. It looks almost like half the distance. So then we wanted to have a component that's almost twice as big as the magnitude of this force to cancel out. So E and D are already out. So D gives 0, E gives, again, a positive torque, wants to cause counterclockwise rotation. We don't want it. C is in the right direction, but it's not large enough, right? It looks like almost the same magnitude as this force at the bottom. B, again, the perpendicular component is in the wrong direction and it's very small. So the only thing that remains is A, and it works. It looks like the magnitude is almost twice the magnitude of the force at the bottom. So we talked about finding the net force, the net torque. We have forces acting at different places, right? And then for each of them, we can find the torque using our formula. And then that allows us to find the net torque acting on any object. One thing that's quite useful to think about is the torque due to gravity. So we can basically treat all the mass as if it's concentrated at the center of mass, so we can replace this extended object by a point particle as far as calculating the torque is concerned at its center of mass, and then we have the total mass m times g there, and we just find the torque due to that one force at that point. So maybe let's try to get a little bit more detailed about this. So torque due to gravity on a rigid body. So again, the picture is we can divide this rigid body into many tiny pieces, and each tiny piece is at some point almost. So let's do that. So let's focus on one of these, right? So that's one infinitesimal piece that I want to focus on. So here is my axis. Here is that one tiny piece. And let's say it has a mass dm. So there's a force dm times g acting on it downward. All right. So then the torque due to this tiny force, if that distance is x from here to here, is, so in this case, it wants to, if x is positive, right, it wants to rotate clockwise, so maybe that's minus, if we're careful about the sign, it's going to be minus x dm g, right? Now, imagine we put a coordinate system like here. So that's really the x component of the position of that little piece. So if you add, so let's call that d tau. So if I add all of these torques, I find the total torque to be an integral let me just factor out the g from that integral. So minus g, an integral x dn. But again, that screams that we have like a definition of the center of mass here, right? And it's an integral over the entire object because I'm adding all those little pieces. So that's just the total mass times the x component of where the center of mass is. So that gives me minus mg xcm, which is basically if all the mass was concentrated at the center of mass, the force is downward, so that's the torque it would give me, right? Because the center of mass is, so this is the axis here. The center of mass is somewhere here. That length is xcm. And then it's like you have a net force that's just mg acting at the center of mass. All right, so now we define torque. So we can, if we know the forces and where they act, and we know where the axis is, we can find the net torque for a rigid body. We can also find the torque due to gravity, just so due to the weight of the rigid body. So we've been talking about like the torque is describes qualitatively kind of the effectiveness of forces in causing rotational motion. But there's actually a very explicit equation, and the way the torque is defined and the way we define the moment of inertia, we can write a rotational analog for Newton's second law. So that's one of the most useful and important equations in the context of rotational dynamics. So again, going back to this table that we've been slowly filling, right? We had, I won't be filling everything, but let's say we had like velocity, angular velocity, acceleration, angular acceleration, mass, moment of inertia, force, and torque. And we already see like there's a relationship between these. So if you have like the net force acting on an object, it gives you its mass on a like point particle. It gives you the mass times the acceleration. And I won't prove this, but a very important equation is, as you can guess, the rotational counterpart of this. So the net torque is the moment of inertia times the acceleration. So that's an equation that we will be using a lot in this course. It's one of the cornerstones of rotational dynamics. It's a relationship between the torque and angular acceleration. So I think that the proof may not be very illuminating. It's basically similar to the proof of showing like the net force is the total mass times the acceleration of the center of mass. So we have to break up the object into a lot of little pieces. So there are some external forces acting on the object that give us external net torque, and there are some action-reaction forces between parts of the object. So that's like internal forces that come in pairs. They don't contribute to the net torque. But let's take this equation to be correct. Again, it can be proved with some work, but I don't think it's very illuminating at this level. So what we want to do is get more practice using these things, right? So maybe as an example, consider the example of a rod that's hinged to the wall, let's say. and we let it go, and it rotates and hits the wall. So we use this to solve a problem involving energy conservation. We found the angular velocity at the end of the motion when the rod comes all the way down and hits the wall. But let's also try to use this to say something about angular acceleration. So released from rest here, and then it rotates down like this. So this is theta. So find alpha as a function of theta. Right, so this rod is rotating around the hinge, it's coming down under gravity, and theta has some rate of change. There's for any value of theta, there's some value of omega, and then there's also some value of alpha, the time derivative of omega with respect to time. So again, as usual, we're saying that the rod has mass m, length L. So in terms of these things, when the rod is at position described by angle theta, what is its angular acceleration? So pause the video, take a piece of paper, and try to find this. So the strategy is, again, to use this equation here. All right. So I hope you managed to calculate alpha. So let's look at it together again. So the rod is rotating around that hinge, right? So the relevant moment of inertia is the moment of inertia for the axis that goes through the hinge. And this we calculated before. We can also look it up in the table that's in the book. So that's 1/3 ml squared. All right. Now, so to find alpha, we can write it as torque, net torque divided by I. So what is the torque, right? So if I draw a free body diagram, well, there are, let's go to this arbitrary position at angle theta. There are some forces acting at the hinge. I don't know, maybe some vertical force, some horizontal force. There's definitely no torque at the hinge, assuming there's no friction there. And then the only other force is gravity, which is downward, and it's mg. Okay, so these forces that go through the hinge, they don't do anything. I mean, by not doing anything, I mean they don't have a torque around the hinge because the distance is 0. And what is the torque due to? And there's no other force, right? There's gravity, there are some contact forces at the hinge. The torque due to the weight of the rod around the hinge is, I can again calculate the component of this distance along the direction of the force. So from here to here, I have L/2, right? The center of mass is in the middle. And then this length from here to here is going to be L/2 cosine theta. So tau for me becomes mg L over 2 cosine theta. And then we're done. I mean, if you want to be careful with the sign, we can just say in words that it's clockwise, but you can also put a minus sign, just so the sign speaks for itself. Then alpha becomes, right, the rotation is this way, right? It's causing acceleration in the clockwise direction. So alpha becomes minus mgl cosine theta 2, the 3 goes upstairs here, ml squared. Just plug in the I and the tau in this equation over here. So the m's cancel out. I get minus 3/2 g over L cosine theta. Cosine theta. Okay, so that was one example, kind of combining these things to find the angular acceleration. Let's do one more example. So this is a quick question for you. Again, pause the video, try to find the correct answer. Okay, so what is the question asking? There's a puck that rotates on a horizontal, in a horizontal circle on a frictionless table. So we're looking at it from above, and someone gives it a quick push, and then it's moving after the push, right? It's connected to a frictionless pivot. So what can we say about the puck's angular speed, right? So after the push is over, right, there's only one force acting on this puck. And let's say that's just a string. So it's going to be in the radial direction, right? So the force is in this direction. So that force goes through the pivot, right? So the distance between the direction of the force and the axis of rotation is 0. So there is no torque, right? The only force that's acting on this puck gives us 0 torque. I mean, of course, there is like going into the board, there's gravity downward, and coming out of the board, there's like a normal force from the table, but those cancel out, and they're not going to cause rotation around this axis. They're kind of parallel to the axis. So yeah, so the only in-plane in this two-dimensional, on this two-dimensional surface, the only force is the tension, and that gives us 0 torque. So the angular acceleration of the object must be 0, and that means its angular velocity cannot change. Okay. All right. So this is another problem. So example 1211. Can read through this and try to solve it. Okay. So what is the problem saying? So we know the torque applied by the engine, kind of at the center, close to the axis, at the center of this rod or this this propeller, which, as the model says, we can approximate it by a rigid uniform rod. We know the torque, we know the length, we know the mass, and the question is, how long does it take the propeller to reach 200 RPM, rounds per minute? All right. So let's go back here and try to do this together. So example 1211. All right, so these are the parameters of the problem. We know the torque, we know the length, we know the mass, we know the axis of rotation that's in the middle of the rod, and we want to find out how long it takes for this propeller to reach 200 RPM, right? So RPM, rounds per minute, that's just the angular velocity in some units. So let's first write it in standard units. So we want to see what is omega in radians per second. So each full round, as you go around, you cover an angle 2 pi, right, in radians. So from here to here is 2 pi. So 200 RPM is equal to 200 times 2 pi, that's the angle covered in radians, per 60 seconds, right? So if you cover that angle in 1 minute, that's covered in 60 seconds. So if you divide it by 60, we find radians per second. So let's see what it is. So that's 400 divided by 6, which is 200 divided by, that's 40 divided by 6, which is 20 over 3. Yeah, that seems right. Okay. And that's per second. Okay, so this is our omega. And in SI units, we can write it like that. Now, to figure out the time it takes to reach from 0 angular velocity to this angular velocity, we just need to find the angular acceleration. We know we have a constant force, so we have a constant angular acceleration. So if you just find that angular acceleration, we can write omega is alpha times t, so t is going to be omega over alpha here, right? The axis is through the center of, the axis is through the center of mass of the rod. That's the axis. So the relevant moment of inertia, I, is going to be 1 over 12 if we look up the correct expression in the table of moments of inertia, times ml squared. And we know that tau is equal to I alpha. The rotational counterpart of F is equal to ma. So alpha becomes tau over I. So we have this. So let's say then combining this 1, let's say, and 2, we find t is equal to omega over alpha, which is tau, then times I. And then I was 1 over 12 ml squared. So t, the time it takes to reach angular velocity omega, is omega over the torque tau 1 over 12 ml squared. Now we just plug in the numbers. So all these numbers are in SI units. The torque given to us is Newton minutes, L is meter, mass is kilogram, and omega was given as RPM, so we just converted that to radians per second. So plugging all of that in should give us the time in seconds in SI units. Let's see, let's try to do the number actually. So I think T, the time it takes to reach 200 RPM is 1 over 12. Omega, we found it to be 20 pi over 3. 20 times pi over 3 divided by the torque, so there's going to be 1 over 60. Mass is 40 kilogram. Length is 2 meters, so that's 2 squared, which is 4. Yeah, so then what is this? So let's say we cancel the 4 by 12, we get 1 over 3, so times that other 3 is a 1 over 9 here. Then let's say cancel the 60 by 20, so we get another 1 over 3 here. Still have the pi. And then we have a 40 times nothing, right? We already canceled that 4 by that, so it's 40 times 40. So this seems to be 40 pi over 27 in seconds. Yeah, pi is roughly like 3.14, so that's, yeah, 120 something divided by 27. So seems to be like 4 point something if I plug it into a calculator. Let's see if we found the correct answer here. So if I look at the slides. Right, so I mean, we can also calculate everything numerically as is done here. So I is 1 over 12 ml squared, alpha is tau over I, and then, yeah, we convert RPM to rads per second, so 200 turned out to be 20.9 if you put that factor of pi. For us, it was, yeah, I mean, yeah, 60 point something divided by 3, so that seems to be right. All right, so yeah, so that's the answer. So trusting what's here, it's 4.6 seconds, so that's approximately, let's say, 4.6. All right. Yeah. Okay. So in the last few minutes, I want to talk about constraints due to ropes and pulleys. So many problems on rotational motion involve pulleys. That in 161 we always assumed all these pulleys are massless, but now that we know about rotational dynamics, we can solve more general problems where the pulley itself has some mass and there's some rotational kinetic energy, for example, associated with the pulley. The pulley accelerates, there are torques applied on the pulley. So we can kind of solve more general problems. the first thing is there are these kinetic constraints. When things move together and they don't slip, various kinematic quantities become tied together. Okay, so let's first think a little bit about what does it mean to not slip, right? So one like everyday situation is, imagine a bad snow day and you're walking on a very slippery, icy walkway. So when we walk, right, we have one foot on the ground and we lift another foot and put it ahead of us. There is this one foot in the back, right, that's stationary on the ground, right? When you're taking a step, one foot is on the ground, it's there, it's not moving, and your other foot is moving in the air, and then you bring it forward, you put it down, and then this foot that's forward now becomes stationary. Now you lift your other foot. So all of that is good, but that requires some friction, right? So this foot that's on the ground when you're taking a step, when your other foot is not on the ground, it's moving forward, the friction from the ground is not letting it move back, right? And if there's not enough friction, if there's a lot of ice, maybe you slip. So that's exactly like this relative motion, right, between your foot and the ground at the point they're in contact. So not slipping really means no relative motion at the point of contact, right? Just to think a little bit about what it means to not slip. Or if you have a rope that wraps around the pulley like this here, and let's say some mass is attached to this rope and it's accelerating downward, and at the same time the pulley is rotating. When we say they're not slipping, means there's no relative motion, right, between the pulley and the rope. So let's think a little bit more about this. So constraint on ropes and pulleys. Right, so this pulley is rotating, let's say let's say at some instant in time, it has angular velocity omega. And there is a rope that's wrapped around this pulley, right? And it's not slipping. So it means if I focus here, let's say I look very closely to that point, here there's some contact between rope and the pulley, and then once you go down, you lose contact. But at this point, if I look at a tiny piece of that rope, well, instantaneously its position is changing with some rate. So instantaneously it has some velocity omega. This point, sorry, some velocity v, rope at the point of contact. This point that belongs to the pulley also have some velocity at that point. So if there's no slipping, they're moving together. There's no relative motion between them. So these two velocities must be the same, because if they're moving with different velocities, then they get separated, right? They slide or slip. All right. So that gives us this constraint that now the pulley is a rigid object, right? So now going back to the pulley, I look at this point, it's rotating with instantaneous angular velocity omega. The velocity of this point, again, is going on a circle. So we talked about this, that the velocity is, at that point, is r, the radius of this pulley, times omega. And then if there's no slipping, this is equal to the velocity of the rope. Now, we can also take a derivative, right, of this. And the time derivative of the velocity of rope is the acceleration of rope. And that's equal to, r is a constant, and the rate of change of omega is alpha, the angular acceleration of the pulley. So I think that's a good place to stop. So next time we'll continue with this discussion and try to work out some examples.